Hello, welcome to the Ultimate Physics channel. The topic of this video is, can a particle have zero mass? Does special theory of relativity allow for that? The answer to both of these questions posed in the title is yes. So let me just start with the answer. I am going to show through the equations of special relativity that the answer to both of these questions is an yes. Right, let's proceed to do that. We know that the total energy in special relativity, E, let us call that, is given by the expression gamma mc squared, where gamma is the Lorentz factor, given by 1 over square root of 1 minus v squared over c squared. Therefore, I write E is equal to mc squared over square root of 1 minus v squared over c squared. Okay, right. So this is the expression for total energy in special relativity. So I squared both. I take square on both the sides. So I get E squared on the left side, m squared c power 4, 1 minus v squared over c squared. Right? In special relativity, we also know that the expression for momentum P is equal to gamma mv, which is equal to mv over square root of 1 minus v squared over c squared. So again, I take a square on both sides. So I get p squared is equal to m squared v squared over 1 minus v squared over c squared. If I multiply both sides by c squared, I get p squared c squared is equal to m squared c squared v squared over 1 minus v squared over c squared. Right? I call this equation 1 and I call this one as 2. So if I do 1 minus 2, that is I subtract 2 from 1, I get e squared minus p squared c squared on the left side, and on the right side I have m squared c power 4 minus m squared c squared v squared over, the common factor is 1 minus v squared over c squared. So on the right hand side, if I take m squared c power 4 outside, I get 1 minus, again, v squared over c squared on the numerator, and the denominator already has the same term, that is 1 minus v squared over c squared. So we can cancel these two terms. Therefore, our left hand side has e squared minus p squared c squared, whereas our right hand side has m c squared whole squared. So this term has been written this way. So now I can say that the total energy squared is equal to mc squared whole squared plus p squared c squared, or the total energy alone is equal to square root of mc squared whole squared plus pc whole squared. And this is the expression that connects energy with rest mass energy and the momentum in special relativity. Now, this energy is very significant in special relativity because this expression tells us that even if mass is 0, the first term can vanish, become 0, and then the energy becomes equal to Pc. That is, if m is equal to 0, we get E is equal to simply Pc. This is the expression for energy. And that tells us that it is possible for a particle to have 0 mass, but still it can possess energy as well as it can have momentum. This possibility arises because of this particular equation, and therefore we got the answer for this question, that can a particle have a 0 mass? Yes. Does special theory of relativity allow for that? Yes. Let us just briefly discuss the examples. What are those particles that have 0 mass but that can have energy and momentum? Let us discuss some examples for 0 mass particles. Our first example is the photon, the well-known photon, which is quanta of light or the electromagnetic radiation. So this is the particle that is exchanged in electromagnetic interactions. And so it is therefore the mediator of the electromagnetic force. So when an electron interacts with, for example, a proton, or a proton interacts with a proton, or an electron interacts with another electron, a photon is exchanged. So it is a mediator of the electromagnetic force. The mass of photon is 0 and it has a spin 1. So it is a scalar boson. Our next example is the gluon. A gluon is another boson, but it is a vector boson, and it is the mediator of the strong force between quarks inside the nucleus. The protons and neutrons within the nucleus are in turn made up of quarks. These quarks interact with each other through the exchange of gluons, and the force that exists between these quarks is called as a strong nuclear force. The gluons have spin again mass 0, but again spin is 1. And then our final particle is the graviton, which is right now not a confirmed particle. There are only theoretical speculations regarding the existence of graviton. If at all such a particle exists, a graviton, if experimentally confirmed, would be found to be the mediator of the gravitational force or gravitational interaction between objects with some mass, right? So it is mediator of gravity. It is another vector boson whose mass is 0 and the spin in this case is 2. So all the 3 particles with 0 mass, all the massless particles are basically bosons. While the photon is a scalar boson, both the gluon and graviton are vector bosons. So these are some of the examples of particles with 0 mass. So again, we know that special theory of relativity does allow for massless particles. So massless particles can exist, and these are the examples. Thanks for watching.